Hello everyone, my name is Sergey Nosov. Today I want to talk with you about a topic that is both foundational and surprisingly deep in C#, generics. Even though many of us use generics every single day, working with lists, dictionaries, or link methods, we don't always stop to reflect on why they exist, what problems they solve, and how we can use them most effectively. By the end of this session, you'll have a clear picture of these 5 key areas. We'll explore the historical motivation, compare with JavaScript and TypeScript, understand what makes C# generics special, learn some advanced constraint techniques, and develop a realistic sense of when generics are the right tool and when they are not. Let's roll back to the early 2000s, .NET 1.0 days. If you wanted a collection of items, you had array list. On the surface, it seemed fine, but there was a major catch. Everything inside the array list was stored as an object type. You can see the pattern on screen. When you added a value type like an integer, it had to be boxed into an object. That's an extra heap allocation. When you pulled it back out, you had to unbox it and explicitly cast it back to int. And if you made a mistake with that cast, runtime error. This approach created 3 major problems. First, it was error-prone. You had no compile time safety, so mistakes weren't caught until your code was running. Second, it was inefficient. All that boxing and unboxing created performance overhead. And third, it was verbose. You constantly had to write casts everywhere. How many of you have debugged a casting error at runtime? Yeah, we've all been there. So, when .NET 2.0 arrived, generics solved these problems elegantly. You can see the difference on screen. Now the compiler enforces type safety at compile time. If you try to add a string to a list of integers, you get an immediate compiler error, not a runtime surprise. And there is no boxing overhead for value types. The core motivation was simple: type safety and performance. Now, I know many of us here are also comfortable with JavaScript, so let's make a quick comparison. In plain JavaScript, generics don't exist. Everything is inherently dynamic and loosely typed. The identity function on screen works with numbers, strings, arrays, anything. But JavaScript doesn't enforce type safety. It just doesn't care what you pass in. In TypeScript, which many of us use daily, we do get generics. You can see the familiar angle bracket syntax here with the generic type parameter t. TypeScript enforces type safety at compile time, or really at transpile time. So TypeScript generics behave similarly to C# at the surface level, but here is the critical difference. Once the code runs, those types completely vanish. They are erased. This is where C# pulls ahead in power. Let's look at the comparison on screen. In TypeScript, generics are purely compile time constructs. At runtime, they don't exist. Everything is just JavaScript objects. There is no escaping the dynamic overhead. In C#, generics are a runtime construct. The common language runtime actually generates specialized versions of generic types, especially for value types. This is crucial to understand. At runtime, a list of integers is not the same as a list of strings. The CLR creates different implementations. For value types, you get specialized implementations that avoid all boxing overhead. For reference types, they share a single implementation, but you still get the type safety benefits. Anyone want to guess why reference types can share an implementation? Right, because they're all just references, same size on the stack. So, while TypeScript offers a developer-friendly safety net, C# generics are baked into the runtime, giving them much more power and performance. One of the most powerful features of C# generics is constraints. Let's look at the generic repository example on screen. Here, we're saying two things about our type parameter t. It must implement the identity interface, and it must have a public parameterless constructor. That second constraint, the new constraint, is what allows us to safely instantiate the t inside our method. This gives us both flexibility and safety. We can use this repository with any type that meets those requirements. C# offers several types of constraints. You can see the most common ones here. You can require a value type, a reference type, inheritance from a specific base class, implementation of an interface, a parameterless constructor, or even unmanaged types for high-performance scenarios. And you can combine them. This processor class on screen requires T to be a reference type, implement iDisposable, and have a parameterless constructor all at once. This is the sweet spot. We get the flexibility of generics, but we still have control and safety when we need it. Now, let's talk practicality. Where do generics really excel? Collections are their bread and butter. Lists, dictionaries, all of those. They're perfect for algorithms that can work with many data types. They're excellent for design patterns like repositories and factories. LINQ is built entirely on generics. And they are great for strongly typed utility methods. But generics aren't always the right tool. You can see some warning signs on screen. If you're writing lots of type of T checks or runtime type inspection, generics might not be the best fit. Deeply nested generics like the dictionary example here get messy fast. Just because you can doesn't mean you should. Has anyone ever encountered a generic type definition so nested you had to read it 3 times? We've all been there. Sometimes traditional inheritance or composition is simply clearer than trying to stretch generics to fit. And you definitely want to avoid over-engineering simple scenarios. Think of generics as a scalpel, not a sledgehammer. Use them for type safety and reusability, but don't force them into places where clarity suffers. Now, here is a particularly important caveat that a colleague recently reminded me of. Reflection and generics don't mix well. Look at the code on screen. If you find yourself using reflection to access properties or methods on a generic type, you've just thrown away the performance benefits of generics. The getValue method returns an object, and if T is a value type, like int or double, You're right back to boxing and unboxing, the very problem generics were supposed to solve. Even worse, you've lost type safety. See that set value call? It compiles just fine, but it can fail at runtime if you pass the wrong type. Reflection uses strings for member names and works with object types, so errors that generics would catch at compile time now become runtime failures. You can see the contrast clearly here. When you combine reflection with generics, you lose performance, type safety, compile time checks, basically all the benefits we've been talking about. So what should you do instead? Consider interfaces, base classes, expression trees, or even source generators. These alternatives give you flexibility without sacrificing the advantages that generic provide. The lesson? If you need heavy reflection on a generic type, ask yourself, are generics even the right tool here? Don't use generics just because they seem sophisticated. Use them because they solve your specific problem better than the alternatives. So, to wrap up, here are the key points to remember. Generics were born out of a need for type safety and performance, and they deliver on both. JavaScript and TypeScript offer lightweight versions of generics, but in C# they are part of the runtime, making them far more powerful. With constraints, we can carefully shape what our generic types allow, and generics are fantastic for collections, algorithms, and reusable patterns, but they are not appropriate for every scenario. The more comfortable we become with generics, the more expressive, safe, and efficient our code will be. Thank you all.